Good morning. Good morning. Good morning. Good morning. There they are, the triumvirate. You know what? Remind me. Remind me, I will open a portal, another point portal for waiting in the waiting room before class even because good morning, yes, and there are some of you, and you know who you are, who totally are like ready and waiting to go before I even like sometimes before I even turn on the Zoom link, and I'm aware of it, and I'm not saying anybody has to do that, but talk about a way of participating and engaging. So you know who you are, Vincent. So that's awesome. So honestly, you can text me whatever, remind me to open up a portal for that, for points for that. But okay. So yes. Good. Oh, thank you, Mary. Oh, maybe I should open up a portal for people who are asking how I'm doing. No, that's inappropriate. But it's not inappropriate to ask. I'm doing well. Yes. Well, I'll admit I'm actually struggling a little bit to tell you the truth. So I apologize in advance if I'm beginning to fall a little bit behind on things like grading and maintaining perfect energy level for class. I'm doing fine. Thank you, Marion, for asking. Seriously. I will admit it's starting to catch up with me a little bit. This chemo is cumulative. So, but yes, thank you. Okay, enough of it. But thank you, Marion. But thank you for being so early. Good morning, Vincent. You know who you are. That doesn't even make any sense. Good morning, Jean. I know who you are. That makes even less sense and is creepy. Good morning, Vanita. I'm gonna leave it at that. Good morning, Melanie. Melanie. Um, Also early, and I appreciate it. Oh, good. I like the direct. Oh no, no, thank you, direct chat person. I appreciate it. No, and I'm just kvetching. That. Oh, thank you. That's very kind of you, direct chat person. And there's two people, both of you in the direct chat. Thank you. I appreciate it. Good morning. There's okay, but I'm just all right. I'm just being, what do they call it in this decade? Vulnerable. We didn't have vulnerability when I was growing up. We just had exposure. Just kidding. All right. Good morning. Oh, thank you. Okay. Good morning, Gabriel. And good morning. Oh, and Annie. Good morning. The animation. Wait, that's a new background, I believe. All right. Anyway, yes. Good morning, both of you, everybody. Um, I have also, okay, we should just get going. I mean, just so you know, I just want to be clear. Okay, am I really wasting time? Yeah, you can tell I'm not feeling perfect because I'm like distracting myself. Okay, we're gonna start in a second. Um, I mean, just to be clear, I just want you to know, I want you to know that teaching and learning is a two-way street. I learn as much from you guys as you learn from me, and that's a fact. So just so you know, even my avatar has been updated to reflect the recent effects of chemo. I mean, see, even my avatar shaves, just so you know. Okay, so I can do that too. And I know what happens when I walk away from the desk to my avatar. Nothing happens. I know. All right, anyway. Okay. Yes, good morning, Annie. Awesome. Okay. I mean, good morning. And good morning, Vicky. Okay. Good morning. Yes. Okay. Um, yes, I am a little bit scattered today. All right, so I have to discipline myself. Inside voice, or outside voice. So, okay. So today, quick reminders, quick logistics. Where's the board? Um, Boardy. Okay, yes. Um, just to remind you, I hope this is clear to everybody. Like, as of tomorrow night, somewhere before 8 p.m., no later than 8 p.m., I will post the actual midterm. You know this. This is just a reminder. I'll post the midterm. Then you take your time and do it over the weekend and do it with whatever sources you want. You do a rough draft. I'm telling you, give yourself time, do a rough draft, even if that's with friends or with Khan Academy or with old videos of mine, whatever. But then you give yourself time to make a final copy of all your solutions to the midterm exam, right? This is just a reminder and review, so there's no confusion. Same way we always do the homeworks and all that kind of stuff, like blank white papers, that treat as though they are a blue book on blank white pieces of paper or something. You fill out all the solutions to all the problems that you do for the midterm. You don't copy and paste my questions. You don't include my questions, but in the document that you make it 100% clear what the question is, and what question you're answering at any time by doing the 5-step method, right? Like you'll have diagrams, you'll make the question 100% explicit, you'll show tons of work in steps 3 and step 4, etc. Ideally, you'll even label your steps. I don't see why you wouldn't, right? And by the time you're done with your final copy of your exam, even if you've gotten tons of help from your friends, from the internet, etc., by the time you're done with your final copy of your exam that has your name on it, then no matter where you got all your information to learn the physics, by the time you finish your whole personal copy of the exam, you have written down a ton, right? You've overwritten, you've overpresented all your thoughts and all the work. Like you've used the 5-step method as a skeleton for showing all your thought process on everything. You've written down a ton, but you've only written down things that you actually understand, right? This is just a reminder summary for this exam. You've only written down things that you understand. It doesn't matter whether statements are true. That's not a sufficient reason to write them down. You're writing down statements that you understand. And your job is to show that you understand them by breaking them down to as many steps and explanations as possible. The more you understand all this stuff, the more you'll see that your personality and your personal way of understanding is going to come through. Like, in fact, that's another reason to do rough copy first and then a final copy. Like, you can do rough copies with friends and all that. You can. It is not cheating. It is encouraged, right? But you'll know that you really get this stuff. But by the time you're doing your final copy, your copy is going to look very different from your friends, even though it's going to have the same true physics. It's going to be your way of understanding it. It's going to have different colors. It's going to have thought bubbles, whatever, annotations, right? It's a presentation, the final thing. It's not just a list of answers by any means, right? It's probably going to be a little bit long. That's my problem. And by the time you submit it by 10:50 a.m. Monday, like what you're submitting to me is a document that I can go through and give you tons of points for. I can go through and grade it without looking at anything else. Like I don't have, or in theory, some other physics instructor could grade it. I mean, that's not going to happen. I'm going to grade it, but like you've written it so thoroughly that I don't have to go back and forth between your document and the original questions to see, like, wait, in part C, like what is she answering again? Like, is there supposed to be a negative sign here? Like, was there a negative sign in the question? Like, no, you're going to make everything. In other words, your document is self-contained, self-sufficient physics, right? By the time you're done, it's just a full walkthrough, a written walkthrough of all this physics derivations. And I don't need, and it's not in response, by the time you finish it's not in response to any other document that I mean, it is, but you know what I'm saying. I don't have to look at any other document in order to be able to efficiently and enthusiastically mark up your exam. And you just are getting tons and tons of points for every step that you include. The more you break it down, the more you write, the more points you're getting, even if by accident some answer is wrong or something like that. I think this is all clear to everybody, but this is just a last reminder because this is the first time we're taking an exam together, right? And so again, your job is to present your full understanding to me that you have fully acquired by the time you sit down to write this. It's not cheating to be continuing to learn this weekend. That's not cheating. What is cheating is to write down things that you still don't understand. Oh, and sorry. What is cheating is to write down things that you don't understand, like that you're just lifting from someone else or from the internet. And again, believe me, I can tell the difference. Flip side of that too, just another reminder, strategy wise, if by the time you're getting to write this final thing down, like if there are still things that you just like honestly don't get and you're confused by, you're going to break those things down as much as you can. And you're going to honestly report while you're breaking them down. Like this thing right here, I still don't get. I feel like it should be blah, but apparently it's blah. Like, so bottom line again, in a way, when in doubt, first of all, when in doubt, write more, not less. But second of all, when in doubt, authenticity is, in a way, what you're being graded on. If I hope that makes it more like, it's not an IQ, and no one's expected to be Newton or Einstein here. It's a test of learning physics. So the more honestly you portray the inner workings of your mind on this, the better it will be. Okay. It's a test of how much you're progressing in fluency in the language of physics. So express yourself as clearly and as fully in our in developing language of physics as you can. Like, don't lie, is what I'm saying. And if there's something that you're really still insecure about, honestly report the insecurity in as much physics terms as you. Okay, you get what I'm saying. All right. So that's what's going to happen for Monday. We're going to get to it now, more practice right now. And also, again, the reason I have to be strict about all this, I mean, we've never had an exam together. This is our first exam together. I'm not trying to make it more stressful. I'm trying to make it as clear and unstressful as possible, but it is serious. And since a lot of my systems and rules are new to people or are maybe hard to predict, let me also be clear that one thing I am strict about an exam is the timing. So you're going to turn it in by 10:50 on Monday, and then you're going to show up to class 10:50 on Monday. I mean, Zoom class, right? Like that's part of the exam experience, that it comes in on time and you show up on time. I've mentioned that. If worst case scenario, if you experience an issue this weekend, any one of you, if there's a medical thing or a psychological thing or like a family, if something is coming up this weekend and you start to anticipate that there's going to be a real problem getting this thing in on time, it is and you're not sure if it's a legitimate reason or not, or this or that, I'm telling you right now that the best thing you can do is reach out to me and communicate with me. Like, let me make the decision with you or see how I feel about it. If you anticipate there's going to be an issue turning this exam in, you as an individual, okay, I'm not like changing the rules, but if you as an individual are going to have an issue, reach out to me and give me a heads up and we'll see what we can do. But the best thing you can do is like, don't surprise me on Monday with it. I'm sure you understand what I'm saying, but making it clear, okay? When in doubt, communicate with me during the weekend if there's going to be an issue. I can't answer questions about okay. And if there's anything unclear in the exam, you can feel free to, if something is unclear in a question or you think there might be an error, also reach out to me. If there's an error, I'll publicize it for everybody, whatever. I'm okay. I won't be able to like, but if it's not, but I'm not going to help people with the exam during the weekend. But if you think there's something unclear, obviously reach out to me. Okay. All right. So that's hopefully that's, is there anything, hopefully that's clear. Okay. Just raise your electronic hand if we're on the same page here with this exam business. Like if the basic, okay. Thank you, Miriam. Thank you, Benita. Thank you, Vicky. Thank you, Annie. Okay. I think that's good. Okay. Thank you. Who's that? Gabriel Jean. Thank you, Gabriel Jean. Okay. Okay. Now, so we have one more day to sort of prepare for it now. And again, it will be, taken from your practice exam. It'll be very similar to this practice exam. It will not be longer. It will not have anything on it that isn't on the practice exam. Some things on the practice exam may not make it to your real exam. Like your real exam will be no longer and possibly shorter than the practice. Also, your real exam may have choices. Look out for if it has choices, just whatever the rules are about choices, take them explicitly. Okay. Okay. Now I have a plan for today. Um, and what's on the board right now is a reminder, like do the 5-step method as a minimum, right? And label your steps. It's just if you label your steps as you go, you're basically grading your own exam as you like. It's like a checklist rubric for grading. If you know that every step is there every single time, you, you're doing okay. You get my point. What you don't want to see on your exam is www, right? Remember, I think this came up the other day. www means like, what, why, where is this from? That's what you don't want to see me write on your exam. That means you've pulled something from somewhere and you haven't justified it sufficiently. That's what we're not looking for. All right. Now I have a plan for today of going over at least one more problem in the practice midterm to help you. Okay, two things. I'm going to do like one more problem in the practice midterm. I'm also going to warn you, or not warn you, I'm going to alert you that most likely the way this is going to work is that in the other section of your same class that meets at 12:15 today, I will try very hard to do something, some other piece of the midterm or answer different questions. Like I'm going to prep with them as well, but I'm going to try to make it be different material. So I highly recommend that when you're studying or when you're doing this exam, like watch the other class video please, for your own benefit. And I'm going to tell the same thing to them, if that makes sense. Like I'm just going to try to do two different things so I've covered that much more practice with you all. Okay. That said, good. Oh no, but you see what I'm saying? No, no problem. But you get what I'm saying, direct chat person? Okay, no, I'm glad. Right. So I'm saying to everybody, like, what hopefully, pay attention in today's class. And then if you miss anything, like watch today's video again. But also, you're always allowed to do what I'm about to say, but I would highly encourage specifically this weekend, watch the videos from the other section as well, because I will try to cover other problems with them so that you have more exposure to practice between the two. Okay. I think you get it. Yes. Okay. Great. So now I have a problem in mind today that I think would be the right problem to do with you. Like I'm ready to go, but because we still do have, an hour left, I want to start by saying if there are any questions at all from any of you, from any aspect of the practice exam, especially concrete, like focused questions, I would love to answer them now first before I'm going to do a full walkthrough of one of the problems. So if your question is, can you do a walkthrough of one of the problems? Well, yes, I will. And I'm going to choose the one that I think is most strategic for you, or I have chosen. But if you have specific questions like, wait, I didn't like in the exercises, like on the first part, like part A or something, if anybody has any, or you don't understand the rules, please ask now. Like this is, this is a prep period. So I'm going to pause for a second. If there's any issues at all about the practice exam or the rules or anything, I'm going to pause for a second if there's any questions. I don't know if this is a good sign or a bad sign, but no question. All right, you good? All right. Okay. There's no question. I mean, you can even stop me once I'm rolling, but it's always harder to stop me once I'm rolling. Oh, yeah. Okay. Oh, okay. I'm seeing the direct chat stuff. All right. So you guys are ready? So you're ready for me to just go? So I'm just going to go over one of the ones in the practice exam, like right now. You ready for me to do this? This works? This makes sense? Can I see? So could I see okay. Thank you, Hudson. Hudson's the man. All right. That's good enough for me. All right. So the following problem is dedicated to the McNulty family. Okay. Okay. Here we go. Hold on. Well, I'll screen share and show you which one. I'm doing this one. Hold on. I know it's not screen sharing. Um, okay. So what I'm about to do is this one. Okay. Um, Yesterday, the problem we did was about Galileo's principle of relativity. It was highly computational, right? Vector addition of velocities was yesterday. I mean, Monday, right? A lot of number crunching, a lot of triangles, very computation heavy. For some of you, that's more appealing. For some of you, it's less appealing. Now, this problem, but now today's different. This problem is also about Galileo's principle of relativity. As I've been suggesting, like that principle underlies like everything we do. Um, this one is more conceptual. This one I'm going to do right now. Um, I'm just trying to screen share so you can see the whole. So this is the situation, right? This is a classic problem. This is historic. There's cool stories behind. The man who made up this problem was a Russian American physicist who won the Nobel Prize, George Gamow. Anyway, like I didn't make this up, is what I'm trying to say. Um, and it caused anyway. For this one, you really have to understand. You really have to take seriously Galileo's principle of relativity to do this. If you really understand it conceptually, then you can solve this problem without a lot of computation. It's a hard problem to solve. If you don't really understand the concepts of physics and you just try to plug into equations and stuff, you can solve it, but you have to do a ton of equations and you have to be super careful. And it's very hard. If you understand the concepts, then you can get this right without a lot of computations. So it's a good demonstration of sort of like the difference between really doing physics versus grinding through math. Okay. So again, this problem may appeal to some of you more. It might appeal to some of you less. Um, I just want to see one thing. Yeah, the one thing I want to say, so I'm going to go over it now to show you a different type of problem, but I also want to caution you. Like in some ways, yes, there's less grinding to do when you solve this problem, but this is also a perfect example. Like if this is on your exam or if there's choices on your exam and you end up choosing to do this, and I don't know how that's going to work, I want to caution you that this is another place where you can't just write a couple of lines and say, there you go, there's the answer. Like you really, it's like more of an essay. You really have to use the 5-step method and really walk me through, and you're ready to really show me. Like I'm picky in the grading of this one, just to warn you. Um, okay, for what it's worth. But so we're going to talk about it now. So I'll quickly summarize just in case. I mean, you can see the screen share, but so the whole idea is there's this river, right? And the river is flowing down. Well, by definition, it's flowing downstream, but it's flowing down the page. So that means the water has some velocity relative to the shore, to the land, right? And it's an unknown velocity. We don't know what it is. Then there's this boat that's traveling up the water at some unknown velocity relative to the water, right? So, okay, so you're in a boat, you're paddling against the current, so to speak, right? And you're paddling, or they're paddling, and then you get to this bridge. Now, the bridge is just like a marker. The bridge is just like home base. It's like coordinate y equals 0 or whatever. When you get to y equals 0, and it's where like the experiment begins, like someone starts a stopwatch, if you like, you get, and at that moment, when someone starts a stopwatch and you pass this bridge, a bottle drops out of the boat, right? I mean, that's what it's saying. I'm just translating it. So a bottle falls out of the boat. So the bottle's now in the water. So the bottle starts just floating downstream, i.e., the velocity of the bottle relative to the water is 0, right? It's traveling with the water, as you'd expect. All this is just like natural, what you'd expect, and you keep paddling upstream. At a certain point, 20 minutes above the bridge, like after you've been paddling for 20 minutes, you notice, oh my God, where's my bottle? Like, oh, when we pass that bridge, I dropped a bottle somewhere. Oh, no, 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 no. So you like turn around really quickly, like you take essentially comparatively no time to turn around, and you start chasing after your bottle. So you keep paddling. Now here's the right now. So far, so you start paddling. One thing the problem says that it does not express in that's hard to express in the picture, but a key piece of information that the problem says is that when you paddle downstream now, you continue to paddle at the same velocity, excuse me, at the same speed relative to the water as you were paddling before when you're going upstream. Now you've got to think about that for a second. I'm saying this part is totally reasonable, is totally possible, but it's not something that would automatically happen in life. Like we're specifying. We're saying whatever speed you were ever going relative to the water before, you're continuing to go that same speed. Before you were going upstream, now you're going downstream. It's not a contradiction. We're saying relative to the water, you continue to go the same speed both ways. I.e., now what does that mean in English? It means a couple of things. Number one, if you had a speedometer in the boat that was measuring what you're doing compared to the water, which is frankly the only thing a speedometer could measure, right? If this, or put, what does that mean? So put another way, if you imagine yourself to be like a lily pad in the water, if you were in the frame of reference of the water, watching the boat go by you, then regardless of whether the boat was going up or downstream, you look at that boat and you see it advancing like at some like one mile of water every second or whatever the number is. I feel like the more I'm trying to say this, the more confusing I'm making it sound. But I'm saying, okay, the most literal way I could put this is whatever strength you're putting into your paddles, however much water you're shoving away every time you go like this, it's the same amount, whether you're going against the current or with the current, right? You're putting the same effort in, and advancing past molecules of water the same amount, whether you're going up or down. I hope you're following that. If you really follow, that's a fact of the problem. I'm not saying that always happens in life, but I'm saying it totally could happen in life. It's an important fact in the problem. It is not a numerical fact. It doesn't tell you a number, but it's telling you a fact that your speed relative to the water in this problem is the same whether you're going upstream or downstream. I'm going to say one more thing about it. Obviously, I'm going to solve it in a second. But if you really understand what that means, if you're visualizing what I'm saying correctly, then you would think, then you'd be right to think that means someone standing on the shore watching you would see you advance upstream, like past you. Someone watching from the bridge would see you going up away from the bridge a lot slower than they would see you coming back to the bridge, right? In other words, in one direction, you're going against the current at a certain number. In the other direction, you're going with the current at that same number. So in one direction, the current is helping you, and in another direction, it's not. So for sure, for certain, if you watched from the bridge relative to the bridge or relative to the shore, the boat is going a lot faster coming down than it is going up. Relative to the water, it's going the same speed both ways. And again, this is just a setup I'm explaining, but this is a real test of, are you following this whole concept of relativity? Because if you are, you'll realize that what the person on the seas is different, observes, is different from what a person in the water or someone just floating in the water would observe. And if you really understand relativity, you understand both of those are correct. Neither one is more correct than the other. They're just two different perspectives. Okay, I'm over explaining, I'm sure, but that's the fact. So, and then final fact. Now, final fact. So there's been two facts of the problem so far. Fact number one is the amount of time it takes you between dropping the bottle at the bridge and turning around is 20 minutes. That's fact number one. Fact number two is after you turn around, you continue to go the same speed relative to the water as you were when you were going up. That's fact number two. And fact number three is by the time you reunite with this bottle, you find yourself and the bottle to be 1 mile below the bridge, right? That's what this diagram that you're looking at right now. The diagram is capturing 2 out of the 3 facts that I just said. But the middle fact is a key fact in the whole thing, and it's not really made clear in this diagram. In fact, if you are still managing to listen to me right now as I'm yelling at the top of my lungs, pro tip, when you take your exam, if this problem is on it or you choose to do this problem or whatever, and I'm not trying to trick you, like I literally don't know. I might give you a choice or I might force you to do it. I don't know. But if you do this problem on your exam, pro tip, I'm telling you right now, when you provide your diagram, well, first of all, you're not literally no one is going to just photocopy this diagram. You're going to make your own diagram, even if it's based on this and very similar and blah, blah. But the pro tip is somehow you will show that you've studied and that you're listening to me. If somehow in your diagram, you explicitly draw attention to that middle fact that I just said. That is, I think it's a flaw in this diagram, that the diagram does not express that middle fact. That fact being that you are going the same speed relative to the water when you go upstream as when you go downstream. Okay. Now, those are the 3 facts. The 20 minutes, the 1 mile, and the same speed both ways. So then you reunite with this bottle at the bottom at 1 mile below the bridge. And the ultimate question of the question, like the step 2, the question is, how fast was the water going relative to the shore the whole time? Like the ultimate question is based on these weird 3 facts. The ultimate question is, what is the speed of the current in this situation? Very straightforward question. I mean, it's asking exactly how fast is this water going relative to the land? What's the current speed? Totally reasonable question. Just kind of bizarre that somehow you're expected to get that from these 3 weird facts, right? I mean, in other words, classic example of a problem that is simple, but not necessarily easy. Kind of the opposite of yesterday's problem, I feel, Monday's problem, where that was very complicated, very, very complicated. But if you just go step by step and you study it and stuff, it's not actually conceptually weird. I mean, well, maybe anyway, yesterday's was complex. This one's simple. I don't think either one of them is easy. Anyway, the question is, obviously I'm about to solve this. I'm over talking it, I know. The question is, what's the speed of the current in this problem. That's what we have to solve. And one last thing, like notice you reunite with the bottle 1 mile below the bridge. Like hopefully if you're following everything I'm saying, or if you just follow the facts of the problem, you understand like that would happen, right? You would reunite with the bottle somewhere below the bridge because, right, like once you do, like the bottle's been floating down, the bottle's just in the water, just floating. So it's traveling downstream with the water. But, and you discover that up here above the bridge. So then you turn around. Now you're paddling downstream, right? You're not floating. You're paddling downstream at whatever, at a speed that was high enough that you were able to even beat the current and go up in the first place, right? Um, so you are, so the water's helping you and you're paddling. So relative to somebody on shore, they would see you like zooming downstream, like you're going faster than the water. I hope that's clear. So of course you can catch up to the bottle eventually. Like you would have to be able, like the bottle's not paddling, you are. So you're going to catch up to the bottle. According to this problem, you catch up to the bottle 1 mile below the bridge. And somehow based on that and the 20 minutes and the other fact, we're supposed to be able to figure out how fast the water's going. So that's what I'm going to do right now. I'm going to, right. So the question is, sorry, as you see, the question is relative to shore, what is the speed at which this water flows? So that's what I'm going to solve right now. Um, if this is on your exam, it'll be very similar, but I'll change the numbers. I mean, okay. And again, I'm just going to say, I'm going to just try, my main goal in the next 40 minutes is to show you how to think about it and to get an answer. I'm going to write some stuff down for your sake, but I'm again warning you, it will not be sufficient. If you do this problem on your exam, you can't just literally copy what I wrote and turn it in. I'll know if you've done that. Like you have to use what I'm writing right now, think about it hard enough to really understand the problem well enough that then you can do it your way. Like you can expand and so you're, whatever I write right now, I'm expecting more from you, just to be clear. Okay. But I will still try to write a lot. All right. So I'm going to switch the screen share. Hold on. Sorry. Okay, give me a second. Sorry. And stop. Okay. Wait, what did I just do? Well, okay. Hold on. So this is practice exam, page 5. I know you can't see the board yet. Without a okay. 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 Hold on, pardon me. I'll explain this. Okay. What I've just written here. Okay, this is a quick. So here's step one of the problem, right? Quick sketch on my part. Yours is going to look different. So I've drawn a picture kind of like the one in the test, right? But now notice this is my step one DFP. I'm just trying to create the situation, right? I haven't even asked the question yet. I'm just capturing the facts of the situation. So notice I make a little picture, but then a key part of the whole picture is to label everything and use my labels. I'm trying to use the picture and labels so that every piece of math that I do in steps 3 and 4 and 5, so that every piece of math I do is explicitly defined, like through this step. So I'm not just drawing the picture, I'm like making up a little notation here that from here on in, every time I use a subscript W, it means the water. Every time I use the subscript S, it means the shore. And every time I use the subscript B, it means the boat, right? Hold on, I'm just changing this. And notice further, like those are three objects. Those are the three key objects in the problem. The water, the shore, and the boat. They are the three key objects because they are the three objects that have three different velocities. But the whole key of them is that they are therefore three different perspectives from which to observe this problem. Each one of those objects is like its own frame of reference. You can look at the world from the perspective, from the frame of reference of the bottle, excuse me, from the water or from the shore or from the boat. So now I'm adding in my diagram and to you as a teacher, notice once you're talking about frame of reference, perspective, frame of reference in physics is all defined by velocity. It's not about where something is. It's about how fast it's moving and in what direction. So if I'm using W from here on in to stand for the water, I want to be clear right from the get-go that anything I say about the water's perspective or anything I say from the water's perspective equally applies, identically applies to the bottle's perspective. Like the bottle and the water might not be the same object, but they have the same frame of reference, the same perspective on the universe because they are both moving at the same velocity as each other, right? The bottle is just floating in the water. Anytime the bottle looks at the water is still from the bottle's perspective. Like if it's next to a lily pad or a particular or a water molecule named Fred, then Fred is always next to the bottle, right? Honestly, and vice versa. If you're a little molecule of water or a little lily pad in the water and you happen to see the bottle like right there, then the bottle is always right there. They're moving together. So they're in the same frame of reference. So if I use W from now on, it means the water or the bottle, whatever. Similarly, the shore, the land is a perspective on this whole situation. It's most easily identified in a way by the bridge. The bridge is just like an object attached to the land. But anybody who's standing on that bridge is seeing what's going on the same way anybody standing on the land is seeing what's going on, or someone standing in China. Like it doesn't matter how close you are. It matters what velocity you're going. And I just hope that's clear. And lastly, before I go on, the thing that's really important about this problem that I cannot say enough, like I literally cannot, what this problem is going to try to show us as I continue to solve it is those are three distinct perspectives. Like the land, the water, and the boat are three distinct velocities, three distinct perspectives on the universe. They are all equally correct. Like if you ever are trying to solve this and you catch yourself even remotely thinking, well, whatever that someone's standing on the bridge would, that's what's actually going on. Everybody does that in their, but it's wrong. Like you got to get used to the idea that whoever's standing on the bridge is not any more correct than who's ever in the water or in the boat. It's not like because planet Earth is also moving. right? I mean, it's moving 65,000 miles an hour past the sun. There's nothing about planet Earth that is actually still or actually a correct perspective on the universe. Like, we are not in the year 2000 BC. We do not anymore think that the Earth is the center of the universe and that everything is moving past us. We now understand, and all from Galileo through all of this, what we're now understanding is the Earth is just another rock floating through the world. It's not special. Every perspective is equally legitimate. Again, that's why video games work. You can put anything into first person perspective and it plays out just as correctly as anybody else being in first person perspective. Okay. So that's the way I'm going to do this problem. Okay, so that's my setup. And again, you could stop me anytime because I clearly I'm just like talking a lot abstractly here. But here's my step one to the problem. And yours would be an expanded, more thorough version of mine. Don't just copy. Anyway, that's step one. So now we go to step two. Like, what is the question, right? So the question is, okay, now again, and look, even I'm even boring myself. I know I'm talking a lot, but what I'm trying to do for those of you who can manage to continue to pay attention, what I'm really trying to do is like pro tip the heck out of this for you. Like, if you're managing to pay attention, I'm trying to give you every possible like hint in advance of what I'm looking for from you on this exam. So I'm not writing it all out. I'm trying to talk. So in other words, right here, step two, WIQ, like what is the question? Very, very important. You got to make the question clear. You've got to not just like I know that you know that I know the question. That's not good enough. You have to make the question so clear to me. You have to make it so clear to me that you get what the question is, that you're going to keep your eye on the prize, that all your analysis is going to be driving to the question. So there's various different ways to phrase this question. I'm giving you options right here. Like you could say something like in your exam, like what is the speed of the water relative to the shore? Excuse me. Right. And you could say more about that. Like, remember, what we're trying to teach right here is there's no just such thing as speed of an object. Every object has a speed relative to some other object. Like, that's what we're trying to like realize here. So we're asking, what's the speed of the water? So you can't say, for example, and a lot of people do this. Like, you can't just copy my question. You have to put in your words. But then a lot of people, by the time they put in their words, will just write like, the question is, what's the speed of the water? No, that is not the question. That doesn't mean anything. The water has one speed relative to the boat. It has another speed relative to the bottle. It has another speed relative to planet Jupiter. Like, the question is, how fast is the water going past the shore? Now, some people in English call that the current. So you can put that. Um, or specifically in mathematical notation, is what we're asking is what is the speed of W relative to S if we use our notation from before, right? But be clear and mindful about this. That's the question. Maybe you're even going to put another diagram here. Last thing I'm also saying, again, I'm just anyway. Last thing I'm saying is like the question is what's the speed of the short given everything that we just said in step one. Now, hopefully in step one, you're really, really clear. Don't just cut like Sorry, I'm getting carried away. But in step one, be really clear what the facts of the problem are. So if there's any doubt in your mind as to how clear you were in step one, here you can re-specify in step two, like given blah, 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 the question is bleh, right? You could do that. Okay, last thing. Uh, um, one way you know that you're doing steps one and two like correctly, because I really do, I take them more seriously than you might realize. In fact, especially step two. I'm very interested in step two. Um, so one way you kind of know that you're doing step two correctly in a situation like this is the first time you looked at the problem, which some of you maybe was last night, maybe a couple days ago, or maybe not, some of you never looked at it until right now. But like put it's when you first look at a problem before I start talking or whatever, you know that feeling when you first look at the problem and your head swims and you're like, I don't even want to look at this, and you put it away? I mean, I don't know if you can relate. I can relate. And when you first look at a problem, you're like, I hate physics or whatever. And you look and it's like, oh, there's a bottle and there's water and there's right? And it's fuzzy. And no one wants to hold on to that feeling of like, I don't even get this problem. What is it even saying? But I'm actually telling you, no, get used to holding on to that feeling. Because here's the deal. When you first look at it and you don't really know what it's saying, or you kind of think you do, maybe you even think you do, but now you're listening to me talk and you're realizing that the problem means something different from what you thought when you first looked at it. I don't know if that's ever happened to you. But if it is, if somehow the problem is fuzzy or wrong, and then it snaps into focus once either I'm talking or your friend is talking or you want, like whatever, try to remember that evolution. A lot of this is about knowing your own mind and getting smarter by stretching it. So I'm saying, when you first look at the problem and you don't really get what it's asking, which is true for many of us a lot of the time in physics, when you first look and you don't really get what it's saying, or you think you do, and it turns out that was a misconception, the best way to handle step two and step one is remember your misconceptions or your fuzzinesses, and now write out your words as though you're teaching yourself, or as though you're helping a friend who you know is probably also having that same misconception. Like address the misconception. Like literally in step two, you could say, although it would seem that this problem is saying blah, 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 blah. In fact, what this problem is actually saying is blah, blah, blah. Like, don't throw away your early misconceptions. If you can address something that you didn't understand before, but you feel you understand now, if you can literally address that evolution, then you're really doing something. Pretend you're teaching me how you got from point A to point B. If you can do that, then you really have gotten to point B, and you'll really prove to me that you have. I'm serious. Like anytime you don't understand something, don't walk away from that feeling and try to forget it. Try to remember it and try to think of all derivations and all proofs and all physics problems as an evolution from not understanding to understanding. The more you can walk me through that evolution, like it would seem, right? And you write it objectively, it would seem that the water is doing it. But in fact, if you look at it this way, actually what the problem is saying is blah, 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 blah. Do that. All right, I'm getting, but really, that is another pro tip. And by the way, it's really a pro tip. It's really a reward for anybody who's still paying attention, because if you follow what I just said about as a general test taking strategy of how to take these things that seem stupid and obvious, like what is the question? Like, okay, well, the question is, I mean, I just copied it from the, no, if you can really take seriously the idea of how to tell me what the question is by showing me what the question isn't, and then like moving past that, the reason that's a major pro tip for the whole test, I'm sorry to keep saying pro tip is stupid, but whatever. The reason it is if you're following what I'm saying, you'll realize that that's a really good strategy to do if you feel really strong with the material. And it's also a really good strategy to do if you don't feel really strong with the material. The more you can walk me through an evolution from non-understanding to better understanding, the more you can walk me through an evolution from not understanding to understanding, the better you're doing, no matter who you are. That's your, okay. So think of it as you're teaching me the physics. You're teaching me how you learned the physics. That's okay. You get my point. Anyway, so that's step two. But if you don't get my point, let me know. But that's step two. So now step three. So we know the setup and we know the question. So now we have to start putting down some general principles here, right? Okay. what is the general principle? Like we're not going to use a million equations here. All of those equations with acceleration in them that apply to other parts of the test, they're not going to, there's no acceleration going on here. So none of those equations are going to apply. Um, this is all about constant velocities and Galileo's principle of relativity. So if I were you in step 3 for this, I would go a little nutto with Galileo's principle of relativity. I'm just going to give you an example here. Like I would say, something like, okay, now again, this is just a suggestion. Like, don't just copy my words or whatever. Don't just copy my words, but here's an idea. What I'm saying is the principle that you're going to use to solve this problem for sure is Galileo's principle of relativity. Like the whole point of the problem. And like again, like everything in physics, it's like simple to say, it's simple to memorize, but it's like a lifetime to really like get your mind around and really see how it applies to problems. Okay. Now what I'm saying is what I if I were you and I were solving this problem, again, think of this problem as like an essay or whatever. I would start by saying that the principle here is Galileo's principle. Now, in this class, I'm telling you, in your notes and so forth, we have 5 different ways of saying that principle, 5 forms. One of them is a highly mathematical and itself breaks down into 3 cases. So there's like a lot to say about this principle. Now some of those forms are the reason for the different form, and they're going to get more in this class. Each different form is like a different subtopic or like a different extension or a different way of understanding the principle and applying it to a whole different set of topics of problems. Like I'm basically telling you, each new chapter of physics is like just another new form of this principle, like for real. Okay, now so far we have 5 that could apply to this midterm, 5 ways of saying it. I think some of them apply more than others. I'm not going to write them all out for you right now. I'm telling you, if you're still listening, what you would do on your exam is you would start with the first one. I would write out the first one because that's what they're all based. I would write out like okay, I'm not going to do like I would say like form 1. I would write it out and I would explain it in your words, maybe even give an example. Okay. And then maybe you'll write all of them if you want to go crazy and you have to, or maybe you'll write a couple more until you get to the one that you think really applies to this problem. Okay. But like, again, this is an opportunity for you to show that you understand the concepts of the class. Like, so form 1, form 2, I'm not going to do all that right now. I want to see how you do that. But, your words. Um, so right now, I guess I'll do what, so one thing I think definitely form 1, I'll write, one way to write form 1 is the laws of physics are the same at all constant what the principle is that the laws are the same at all constant velocities. Now, if you just take that at face value, it sounds like, duh, yeah, the laws are the same and all. I mean, of course, but what I'm trying to say here, what I'm trying to get across in the class, what you're trying to get across to me on the exam is, okay, if you take that really seriously, that the laws are the same at all constant velocities, One way of putting that in your own words or in my words here. Okay, now again, I'm going to move on. I'm watching the clock. Uh, these are all examples. Again, the more if you do this problem, the more I see that you have taken the benefits of this recommendations, but done it in your own way within your own words, the happier you and I both are. So like here's an example. So but don't just so if you don't show any recognition of this entire lecture, that would not be good. But if you just like copy my words directly down, that's a giveaway that you're not getting my point. So but here's an example, right? You could write something like what the form number one means in terms of this problem. What it means is that you can do physics in any perspective you want. Like to cut to the chase, and I am watching the clock, I promise, although not as well as I should be. To cut to the chase, we're going to try to solve this problem. We're going to try to figure out what the water's doing right now. The obvious thing that we would do if we didn't know any physics at all, if someone just gave us this problem, we would like stand on the in our minds, we would like stand on the bridge and like watch what's going on. And like, okay, the boat's going like this way and then it's going this way. And we would do a bunch of computations and try to figure out from the perspective of the bridge that standing on the shore, we would tend to think, okay, that's like the natural place, that's the natural way to observe the problem. So I'll like try to solve it from that perspective. What I'm saying right here before I go any further is, well, you could do that. You could do physics from the bridge. But according to physics, if you take it seriously, you could also do physics from the perspective of the boat. You could be the boat watching water go past you and watch the bridge go past you. And you could take measurements and do calculations from that perspective. Or you could take perspective calculations and measurements from the perspective of the water. If you're understanding physics, you'll understand those are three different perspectives. They're going to get you three different, they're going to be three different perspectives, but they're all equally correct. Any answer you ultimately get in one of those perspectives is obeying the laws of physics, and the laws are the same in all the perspectives. So, in fact, any perspective you choose, as long as it's unaccelerated, and they all are, any perspective you choose is correct according to physics. And then the big point of Galileo, the big, not just pro tip for this exam, but pro tip for physics is okay, since you can choose any perspective you want in order to solve a problem, you must make a choice. It's not just that you can. You must choose what frame of reference you're observing things from. Velocity is relational, right? So you have to specify what are you comparing to what. And when you make that choice, you should make it mindfully because all choices will be correct, but some will be more convenient than others. So some perspectives are more strategic than others. That's really what Galileo's principle is really saying. Put it in your words. In my words, I'm saying because of Galileo's principle of relativity, I can choose whatever perspective I want. Let's choose, we have to choose. Let's choose the most strategic reference frame, and I'm using the words reference frame, frame of reference, coordinate system. I'm using them all interchangeably. I mean, perspective, reference frame. Okay, here's the big leap right here. And I am watching the class. I'm saying right, I'm still in step 3 GDP. I'm saying what's the overall principle? The principle is that we can choose any perspective we want. So I'm maybe technically I just moved to step 4. Oh, sorry. So what I'm saying is, you can tell me to go back if I'm step 4. What I'm saying is we will solve the problem from the perspective of, from the frame of reference of the water, from the water's frame of reference, from the water's perspective, i.e., what that means is the water and bottle are still. And everything else is moving, right? This is, we're playing the video game from the perspective of the bottle. We are the bottle getting in first person perspective. So what, right? I'm saying I'm choosing to do that. Am I saying that's the correct perspective? No. But I'm also saying the land is not the correct perspective either. There is no correct perspective. I'm saying that looking at it from the perspective of the bottle is going to be the most convenient, strategic way to solve this problem. And I'm notice, I mean, I am a little bit running out of time, but I'm spending all of this time on the conceptual setup because that is the difficult part of the problem to see and to explain. Once I actually convince you or convince the reader of this conceptual setup, the math is like 2 seconds. I promise. Not 2 seconds, but so what I'm saying now, and I'm going to start hurrying this up, from this perspective, if you get into the perspective of the bottle, which is just floating in the water, what you see all the entire time, right? You see a bridge, like this is a bridge. You see a bridge going up, right? And you see a boat, um uh wait, sorry. Yeah, and you see a boat going up super fast and then coming back down to you, right? But I mean, at first, in other words, if you're the water, you see boat and bridge going up away from you, and you see the boat for sure going faster than the bridge, and then eventually the boat's coming down. I don't know if that's clear enough, but that's the case, right? So why am I doing that, or what does that do for me math wise? Okay, in this sorry, it would be relative to the water, right? That's what I'm saying. Yes, good, Andy. Sorry, I missed 4 minutes ago. Yes, I totally agree with Andy. Relative to the water is what I'm recommending as the way to solve this problem. You're being the water, you're being the watching. So you see this boat, this bridge go up, and you see this boat go up even faster, and then the boat eventually comes down. Now, why am I saying that? Because from this from this perspective, from the water perspective, or from the bottle perspective, same thing. From now, watch this. This is the hardest part. I'm warned again. Thank you for paying so much attention. I know this is a lot, or it seems like a lot about a little. I know that. And I know we only have 10 minutes left, but we're going to solve this within the 10 minutes. But the part I'm going to say now, I'm telling you, is the part that that you got to take really seriously. The part I'm about to say is what you have to explain in your own words and show that you really get it. I'm saying from the bottle's perspective, and only from this bottle's, like, why am I picking the bottle? Like, why did I pick this perspective? Why am I? Because from the bottle's perspective, first of all, remember, remember, this is from step one. We're told that whatever speed the boat is going up compared to the water is the same speed as it comes down compared to the water, right? Again, that's not true compared to the land. Compared to the land, the boat's going up slowly and coming down quickly. And that's true to the land. To the water, the boat is going up at a certain speed, coming down at the same speed. Now, check it, yo, check it. Like, that's a fact from step one. But also, from this perspective only, what's also true, and you should draw a diagram or somehow is the following. What's also true is the distance boat travels up is the same as the distance the boat travels down. Now that, I'm going to say that what we've 8 minutes. I'm telling you right now, your reward for paying attention to this whole slog is that you will know that this part right here is where you want to put all your elbow grease on the exam. You want to make sure that you actually understand what I'm saying right here. Wait. What I'm saying right here is only true in the water frame of reference, and it's why I'm choosing the water frame reference. Let me say it again. It's not true from this. So you need, if you're going to explain this to me, what you have to in the exam, you got to show me why what I'm about to say is true if we look at this from the water perspective, but it's not true if we don't look at it from the water perspective. Like, hence, and what I'm saying is this: if you are lily pad in the water, then the boat goes away from you some distance that I don't know. I'm not saying I know the distance, but whatever that distance is, then like the boat gets to a certain point and then it just comes back to you if you're the lily pad, right? Like the lily pad this whole time might be moving past the bridge. I mean, it is. If you're a lily pad, if you're the bottle, sure, you're moving past the bridge the whole time. So someone on the shore sees the boat go up a certain amount and then go down a huge amount, right? If you're on the shore, if you're on the, oops, sorry. If you're on the shore perspective, you would see something like this. But if you're from the water perspective, that changed. Sorry. If you're in the water perspective, no, you see something like that. You've got to think this through on your own. Make sure you see that you understand both. And they're both correct. Just one is more strategic than the other. If you're on the shore, right, the boat goes up a certain way. And then it realizes it lost the bottle. So it goes back down to the bridge and goes way below the bridge and gets the bottle, right? That's if you're watching from the shore. But if you are the bottle, then you're not moving. You're you, right? So the boat goes away from you and then the boat comes back to you. You're not, the boat goes away to some place and then it comes back from that place. The boat just makes a round trip, an equal round trip if you are the bottle. And if you're saying, but wait, but I thought the bottle was moving. Well, from the bottle's perspective, the bottle's not moving. From the bottle's perspective, the bridge is moving, right? So what does the bottle really see? Again, pretend this is a video game. I'm not saying everybody plays video games, but some people do, right? Or pretend it's a movie, whatever. If you're the bottle, what you see is a boat going up while a bridge is going up, right? And the bridge is going, and then the boat turns around, starts coming to you. The bridge is still going up. Like, yes, I'm acknowledging that there's motion in the universe, but it's not my motion. It's the bridge. It's going away from me the whole time. And during that whole time, the boat makes a round trip to me. You've got to understand, this is the whole key of the problem, that from the bottle's perspective, it's an equal round trip. It is not an equal round trip from the bridge. Therefore, that's too hard. I'm not going to solve it from the bridge's perspective. But if I solve it from the water's, and so again, in your exam, like compare the both. Show me that you understand. But if you understand right now, because we have 5 minutes, I'm choosing the water, the bottle's perspective, same thing. And you got to understand that every time I say water or bottle, it's the same thing as far as perspective is concerned. So therefore, so what? I'm still in step 4 here. Therefore, if the speed, if the speed up equals the speed down in this perspective, and the distance up equals distance down in this perspective, if the speed is up and if the speed up equals the distance, if the speed up equals the speed down and the distance up equals the distance down, then the time up must equal the time down. In this perspective, time up must equal time down. You got to think this through. That's really weird. I'm saying, remember how the fact of the problem is that the boat goes 20 minutes before it realizes that it lost it, before it turns around? Now, the problem doesn't say anything about how much time it takes until the bottle and the bridge, the bottle and the boat reunite. But I'm saying if you think this through, it must be another 20 minutes exactly before they reunite. Again, that seems weird. It seems like, wait a minute, if I was standing on the bridge, you're saying this takes 20 minutes? If you're standing on the shore, the short arrow takes 20 minutes and the long arrow takes 20 minutes? Yeah, I am saying that. Why? Because remember, if you were standing on the bridge watching, then the boat on its way up was going slow. And on the way down, it's going fast. So on the way up, it covers very little ground. Sorry. So on the way up, it's going slow, and on the way, it's going down. But on the way up, it's going very little distance, and on the way down, it's going a big distance. So the times work out the same. But it's easier to see from the water. Both the distances are the same and the speeds are the same. So the times are the same. I'm saying, therefore, I'm saying time back down is also 20 minutes. That is not a fact given in the problem. That is something I just figured out and that you're going to figure out and show me. But I believe we just figured out that time up is 20 minutes. I mean, that was a given. Time down, evidently, surprisingly simple, is also 20 minutes. Therefore, total time is 40 minutes. And we have 2 more minutes of the class, right? Guess what? We're just about done. The entire trip is 40 minutes, right? During this time, during 40 minutes, the bottle, from bottle's perspective, observes the bridge go up how far? 1 mile, because the problem said so. The problem said that when the whole problem is over, the bottle is a mile below the bridge. So from the bottle's perspective, the bottle sees the bridge go up a mile in 40 minutes. So the velocity of the shore relative to the water must be 1 mile per 40 minutes. Or in other words, if you just do the math, like 1 mile per 2/3 of an hour, in other words, 1.5 miles per hour. We're just about done. We have 1 minute. I'm saying I'm saying this is the answer right here. I know it's time. I'm saying the answer is right here. The answer is the bottle sees the bridge go away from it. The bottle sees the shore. The water sees the shore go away from it up at 1.5 miles per hour. Therefore, the shore sees the water go past it down at 1.5 miles per hour. That's the answer. Now, the class is over, but look, if you just look at the calculations I just did two steps. There's just two bits of math. If you just, if that, right, it's because of all the concepts, the math is super simple, but the math is not justified or even understandable without the whole concept. But if you get into the perspective of the water, it's two steps. It's 20 minutes up, 20 minutes down makes 40 minutes. Yes, have a good day. Have a good day. Okay. But right, so the whole answer is 1.5 miles per hour. You gotta understand, you gotta think about it and understand why. I'm done. I mean, I'll hang out for any questions, but that's it, and I'll turn off the recording, but that's so hopefully we got something out of this. But yeah, 1.5 miles per hour. I'm stopping the recording. Thank you.